Okay, let's dive deep into a truly foundational story in mathematics. Imagine a tool so powerful it underpins everything from predicting the weather and understanding gravity to designing roller coasters and creating realistic computer graphics.
We're talking about calculus.
Exactly, calculus. And today, we're not looking at the clean, polished version you might find in a textbook. Oh no. We're going back to its chaotic, messy birth, specifically focusing on the contribution of Gottfried Wilhelm Leibniz.
That's right. And our journey today is guided by, well, a collection of academic sources that really dissect Leibniz's earliest public pronouncements on the calculus. We're looking at three key papers he published in the German journal Acta Eruditorum between 1684 and 1693.
Okay.
Think of these papers as the first glimpses the world got of this revolutionary idea, and as our sources make pretty clear, those first glimpses were, well, they were less than crystal clear.
Absolutely. Less than clear seems like an understatement, from what I gather. So our mission in this deep dive is to understand how Leibniz even conceived of these radical ideas in the first place, why his initial published description in 1684 was so incredibly difficult to understand, almost like a puzzle, right?
Exactly, a puzzle or an enigma.
And then crucially, how this initially baffling concept was cracked open and made accessible and widely used, thanks really to the perseverance and collaboration of a few brilliant individuals. We're aiming to cut through the historical density here to give you a direct line to understanding this pivotal moment.
Yeah, it's a story that shows scientific progress isn't always this smooth, logical march forward. Sometimes it starts with a stroke of genius presented in an almost undecipherable form. And it takes dedicated work from, community to make it truly flourish.
I find that fascinating that something so fundamental, so widely taught and applied today, started life as something described, as you said, as an enigma. Let's pull back the curtain and see how this all began for Leibniz. Where do we start?
All right, let's trace the seed of this idea. Gottfried Wilhelm Leibniz, born in 1646, was an extraordinary intellect, a true polymath. He was active in philosophy, law, diplomacy, logic, history, you name it.
A real Renaissance man, almost.
Kind of, yeah. But surprisingly, when our story begins, advanced mathematics was not his strong suit, not at all. He earned his doctorate in jurisprudence, that's law, in 1667, and entered the service of the Elector of Mainz in 1668.
So law, not math primarily.
Right. And a look at his background from our sources at this time reveals a rather pointed assessment. Despite having already published an essay on logic and combinations, the Arte Combinatoria, back in 1666, his mathematical knowledge at that point is described as, and this is a quote, most deficient.
Most deficient. Wow. That's quite the starting point for the co-inventor of calculus. So he wasn't some mathematical prodigy from childhood then.
Not in the sense of having deep training in the advanced geometry and analysis of the time, no. But he was incredibly bright and, crucially, a very quick learner. The transformative period for his mathematical development was his time in Paris, from 1672 to 1676.
Ah, Paris.
Yes. This is a period of intense study and really some crucial encounters for him.
And the most important encounter there was with Christian Huygens, right? The famous scientist.
Absolutely. Christian Huygens, the celebrated Dutch mathematician, physicist, and astronomer, was residing in Paris at the time. He was a leading figure at the newly established French Academy of Sciences. Huygens recognized Leibniz's sharp mind and essentially took him under his wing, introducing him to the cutting edge of contemporary mathematics. This relationship was pivotal. Absolutely critical.
So Huygens was the mentor figure. Was there a specific challenge or problem that really ignited Leibniz's interest in developing a new kind of math?
Yes, there was. A specific problem posed by Huygens really sparked his focus. It was the problem of summing an infinite series, specifically the series of reciprocal triangular numbers. That's 11 plus 13 plus 16 plus 110 and so on.
Okay, adding up infinitely many fractions that get smaller and smaller.
Right. Leibniz tackled this, and he had a profound insight. He realized that the terms in this series could be expressed as differences of other numbers. For example, 11 is like 21, 11. Oh, wait, no, hang on, it's simpler. 11 is 11, 13 is 11, 23. No, that's not quite right. Let me check the example. Here it is. The terms are differences like this. 11 equals 21, 22. 13 is 22, 23. 16 equals 23, 24, and so on. Each term is twice the difference of consecutive reciprocals.
Ah, okay. So each term involves a difference. Does that make it easier to sum?
It does, because when you write them out like that, it becomes what we call a telescoping series. The second part of one term cancels out the first part of the next term.
Right. So most of the terms just disappear when you add them up.
Exactly. By rewriting the terms as these differences, the sum of the entire infinite series collapsed beautifully. Almost all the intermediate terms canceled each other out, leaving a simple result, too.
And that matched Huygens' answer.
It agreed perfectly with Huygens' known answer. And this success, you can imagine, was incredibly motivating for Leibniz. Our sources emphasize how it fueled his passion for mathematics and led him to explore summing other similar infinite series.
So he got hooked.
He really did. During this Paris period, guided by Huygens, he devoured the significant mathematical texts of the era: Pascal's Lettres d'Edenville, Descartes' Foundational Geometria, Grégoire de Saint-Vincent's work on summing geometric series, and contributions from mathematicians like James Gregory, Sluice, Galileo, and Wallis. He was rapidly acquiring the advanced mathematical knowledge he previously lacked.
Quite the crash course from most efficient to reading the cutting-edge stuff.
A very intense crash course.
So, the spark came from seeing this powerful pattern of terms canceling out when written as differences. How did he take that numerical insight and build a whole new calculus for geometry out of it?
Well, his reflection on Pascal's work, particularly Pascal's arithmetical triangle, what we usually call Pascal's triangle today, led him to construct his own related structure, the harmonic triangle.
The harmonic triangle. Okay, what's special about that?
The harmonic triangle had a key property that really resonated with him. Each sequence within the triangle is the sum series of the sequence immediately following it, and conversely, it's the different series of the sequence just before it.
Okay, hold on. So if you have a row of numbers in this triangle, summing them up gives you the row above it.
Essentially, yes, relating terms across rows.
Mm-hmm.
And taking differences relates it to the row below it.
Got it. Summing goes one way, differencing goes the other.
Precisely. And this structure made blindingly clear a fundamental relationship. Forming different series and forming sum series are mutually inverse operations when you're working with numerical sequences. One operation literally undoes the other.
And that inverse relationship, that sounds like the core idea that bridges to calculus, doesn't it?
It is. That's the absolute kernel of it. The stroke of genius was taking this insight from these discrete number sequences and transposing it to the study of continuous curves in geometry.
How did he make that leap?
He began to think about sequences of points along a curve, their ordinates, their e values or abscisses, their x values, or other geometric quantities related to the curve. And the crucial step, the really big leap, was to imagine that the differences between successive terms in these geometric sequences, say, the differences between two very, very close e values on the curve, were infinitely small.
The infinitesimals. This is where that controversial concept enters the picture.
Yes, this is the moment. If you start to imagine a curve as being made up of many infinitely short straight segments like a polygon with infinite sides, then working with these infinitely small differences becomes incredibly powerful.
Okay, how so? What do these operations mean geometrically?
Think about the geometric interpretations. If you sum up these infinitely small increments, say, you sum up the lengths of the ordinates, the y values, multiplied by tiny, infinitely small steps along the x-axis.
Mm-hmm.
What do you get?
You'd get the area under the curve, right? The quadrature problem.
Exactly. The sum of many infinitely thin rectangles. That's integration. And now what about the difference between two successive infinitely close ordinates? If you divide that tiny difference in y by the corresponding tiny infinitely small difference in x, what does that give you?
Well, that's the slope of the tiny line segment connecting those 2 points,
Yeah.
which, as the points get infinitely close, becomes the slope of the tangent line to the curve, the tangent problem.
Precisely. So the numerical operations of summing and differencing, which he saw were inverse in number sequences, when applied to quantities considered to be infinitely small along a curve, correspond directly to the fundamental geometric problems of finding areas, quadrature, and finding tangent slopes. Tangents.
Wow.
These were central challenges in mathematics at the time, huge open questions. And Leibniz had found a way to unify them and solve them with a single inverse pair of operations.
That's incredibly elegant. But he needed a way to write this down to make it a calculus, a system for calculation, right? That's where the famous symbols came from.
Yes, exactly. He needed a clear, efficient notation to represent these operations on infinitely small quantities. For the summation process, the summing of infinitesimals that gives the area, he chose the sign.
The integral sign.
Right. It's basically a stretched S, standing for summa, the Latin word for sum. Our sources suggest he might have been inspired by Cavalieri, who used the phrase omnes lineae, all the lines, to denote areas.
Okay, for sum, what about the differencing part?
And for the difference operation, the one related to finding the tangent slope, he chose the letter D, just D, symbolizing the infinitesimal difference between successive, infinitely close quantities, like d or dx.
If for the sum, finding areas, finding tangent slopes, it seems so obvious now, but inventing that notation must have been
It
huge.
was revolutionary, and Leibniz himself explicitly linked these ideas later. Our sources include a quote from his letter to the English mathematician Wallace in 1697, where he looked back and stated, "The consideration of differences and sums in number sequences had given me my first insight when I realized that differences correspond to tangents and sums to quadratures."
That's a beautiful, clear summary from the inventor himself. It shows that direct line of thought. Was he developing all the rules and techniques we associate with calculus back then in Paris?
His mathematical manuscripts from the Paris period, which were published much later by C.I. Gerhardt, show him actively building this calculus of differences and sums. They confirm he was exploring and verifying that these operations were indeed mutually inverse. He was figuring out the rules for products, quotients, powers.
The nuts and bolts.
Exactly. He was also deeply influenced by Pascal's traité des sinus du quart de cercle, particularly in the use of what Leibniz came to call the characteristic triangle.
The characteristic triangle. You mentioned that similarity before. How is that key here?
Right. Imagine that infinitely small segment of the curve we talked about. It can be seen as the hypotenuse of an infinitely small right-angled triangle.
Okay.
The two legs of this tiny triangle are the infinitesimal change in the x direction, which he denoted dx, and the infinitesimal change in the y direction, d, or dv, if using v as the variable, as he sometimes did. This tiny triangle, formed by dx, d, and the curved segment itself, is the characteristic triangle.
Okay, so dx is the tiny step horizontally, side e is the tiny step vertically, and they form a microscopic triangle with the tiny piece of the curve itself.
Exactly. And the crucial geometric fact is that this infinitesimal characteristic triangle is similar. It has the same angles and proportional sides to the larger finite right-angled triangle formed by the tangent line at that point, the ordinate, the Khmer value, and the subtangent, which is the length along the x-axis from where the ordinate hits the axis to where the tangent line intersects the x-axis.
Ah, the similar triangles unlock the geometry.
Precisely. Our sources highlight that Leibniz saw the great power and versatility of this characteristic triangle. It allowed him to translate relationships between the finite measurable quantities, like the ordinate and subtangent, into relationships between the infinitesimals, metex and day, and vice versa. It was incredibly useful for solving both tangent and quadrature problems. It led him to deduce results like the transmutation theorem, a powerful technique for transforming certain area problems into potentially simpler ones.
So the characteristic triangle is really the geometric embodiment of the infinitesimal relationships he was working with. It's the bridge.
Yes, it's the crucial link between the abstract idea of infinitely small differences and sums and the concrete geometry of the curve, its tangent and its area. Another strong motivator for Leibniz during this Paris period was the desire to solve the inverse tangent problems.
What are those?
These are problems where you're given some property of the tangent line at every point, like its slope or its length, or where it intersects an axis, and you have to find the equation of the curve itself.
So working backwards from the tangent to the curve.
Exactly. Descartes, for instance, had found these very difficult. Leibniz saw his developing calculus as a potentially much more powerful tool for these. He sought a new, general method with an optimal signs and symbols, system notation, and rules that would make calculations simple, straightforward, and almost automatic, even for these hard inverse problems. He wanted a truly algorithmic approach.
It sounds like by the time he left Paris, he had really developed the core ideas, the notation, and the basic framework. He had the tool.
He did. By 1676, when he left Paris and returned to Hanover to take up a post as court counselor and librarian for the Duke of Brunswick-Lüneburg, he had the foundations of his differential and integral calculus.
Okay, so let's just recap this first part quickly. The core insight came from the inverse relationship between sums and differences in number sequences, sparked by that series problem from Huygens.
Right.
He brilliantly transferred this to geometry using the concept of infinitely small quantities along curves,
Infinitesimals, yes.
which led to the operations of differentiation, the modi for finding tangent slopes, and integration, the a for finding areas.
Inverse pair.
He developed the key notation in D and saw the power of the characteristic triangle as the geometric link between the infinitesimal world and the measurable world.
That captures it perfectly.
It's really remarkable how that single insight about inverse operations blossomed into this whole powerful system. And finding the right notation wasn't just a detail. It seems absolutely crucial for making the method usable, for making it a calculus.
It was transformational. The notation helped make the calculus algorithmic, allowing for systematic calculation in a way that was a major departure from earlier, more geometric or ad hoc methods for tangents and areas. It aimed for that automatic quality he was seeking.
All right, so he's back in Hanover, armed with this powerful new tool developed during those intense years in Paris. When does he finally share it with the wider world? And what does that first public appearance look like?
That brings us to the second section,
Oh.
the somewhat bewildering public debut of the differential calculus. His first paper describing it appeared in October of 1684.
Okay, 1684, so that's what, 8 years after he left Paris?
Roughly 8 or 9 years, yes. The venue was the Acta Eruditorum, which translates as Proceedings of the Learned. It was the first scientific journal published in the German states, founded just a couple of years prior in Leipzig by friends of Leibniz, actually.
The big reveal, finally. After almost a decade of development, what was this initial paper like? Was it a magnum opus, laying everything out clearly?
Well, this is where the enigmatic and obscure descriptions from our sources really come into play. The paper was incredibly brief, only about 6.5 pages in total.
6.5 pages? For the invention of calculus, that's tiny.
Extremely concise, and its title was quite a mouthful. Nova Methodus pro maximis et minimis itemque tangentibus, quae nec fractas nec irrationales quantitates moratur et singulare pro illis calculi genus.
Okay, Latin titles always sound impressive. What's the gist in English?
A new method for maxima and minima as well as tangents, which is neither impeded by fractional nor irrational quantities, and a remarkable type of calculus for them.
That title sounds pretty confident, almost boastful, claiming it solves problems that stumped previous methods, especially with fractions and roots.
It is definitely confident. Leibniz explicitly highlighted in the title that his method differed from and surpassed earlier methods for finding maxima, minima, and tangents, like those of Descartes or Fermat, precisely because it could handle complex algebraic expressions involving fractions and irrational roots with ease. It was a direct assertion of his method's power and generality.
But why was it so brief and, as our sources insist, so obscure? He'd had nearly a decade since Paris to polish the presentation. Why release something so short and apparently hard to follow?
That's a great question, and Leibniz himself offered explanations later on. In some of his writings and correspondence, like a manuscript titled Historia et Origo Calculi Differentialis, History and Origin of the Differential Calculus, he claimed he had indeed developed the calculus in Paris between 1672 and 1676.
Right.
But delayed publication for over 9 years after returning to Hanover, because he was simply preoccupied with other demanding tasks. He mentioned his extensive historical research for the House of Brunswick-Lüneburg, his diplomatic work, his philosophical writing.
Okay, the busy polymath excuse. He had a lot on his plate. That makes some sense, I suppose.
It does, partially. But the sources, particularly drawing on historical analysis like that of H.G.M. Hess, suggest there was a more urgent, even slightly dramatic reason for the hurried nature and the difficult presentation.
Ah, okay. What was the more pressing reason?
It involves another mathematician named Ehrenfried Walter von Schirnhaus.
Schirnhaus, wasn't he a friend of Leibniz from Paris?
He was. They had studied together in Paris around 1675. The issue was that Schirnhaus was beginning to publish articles in that same journal, the Acta Eruditorum, that used methods based on infinitesimals, methods very close to those Leibniz had shared with him privately years before.
Oh.
Schirnhaus published papers hinting at these techniques in December 1682, March 1683, and October 1683, just before Leibniz's paper in October 1684.
So Leibniz saw his friend publishing similar ideas, maybe getting dangerously close to his own invention, and felt a threat, a priority concern.
Exactly. Our sources, referencing Hess's work, argue that Leibniz perceived a real risk of having his unique invention essentially scooped or even stolen. This competitive pressure created a sudden urgency that forced Leibniz's hand. He felt compelled to publish immediately to establish his priority, even if the paper wasn't perfectly polished or fully explained.
Right, get something out there with his name on it, fast.
Precisely. And this likely contributed significantly to its rushed style, its poor organization, its excessive conciseness, and therefore its complexity and obscurity for readers.
So the obscurity was partly a consequence of a hurried effort to stake his claim, but wasn't there also a suggestion that some of the obscurity might have been deliberate?
Yes, and this is another crucial layer to the story. The complexity wasn't just due to haste. The structure and presentation were also made difficult by what appears to be a deliberate strategic decision. The need to conceal or at least downplay the explicit foundation of the calculus in infinitesimals.
Why hide the infinitesimals? They seem so central to the whole idea you just described. They're the magic ingredient, aren't they?
They absolutely are. But Leibniz was acutely aware of the potential philosophical and mathematical backlash from many mathematicians of the time. These were scholars deeply rooted in the rigorous geometric tradition of Euclid and Archimedes.
They wouldn't like these fuzzy, infinitely small things.
Not at all. The concept of infinitely small quantities would likely strike them as philosophically dubious, paradoxical, and certainly mathematically ill-defined, lacking rigorous foundation. Remember, the rigorous foundation for dealing with limits and infinitesimals wouldn't be developed for another century and a half, with Cauchy and Weierstrass.
Okay, so he was worried about getting shot down on philosophical grounds before people even tried the method.
Exactly.
Yeah.
To avoid immediate, potentially crippling criticism, maybe even outright rejection of his method based on these foundational issues, Leibniz seems to have chosen to present the calculus in a way that obscured its core reliance on these infinitely small quantities. He sort of danced around it.
It was a strategic choice then, but one that sacrificed clarity for safety.
That seems to be the case. A choice that undeniably made the paper far harder for his contemporaries to understand and replicate.
So, a combination of being rushed due to competition and intentionally hiding the trickiest conceptual part. No wonder it was called an enigma. Let's look at the content itself. What was actually in this difficult 6-page paper?
Okay, the paper operated within the geometric style common at the time, following the Cartesian tradition.
Yeah.
It talked about curves, reference to axis, and x-axis was explicitly shown, variables like abscissas, x, and ordinates y or v, and finding tangents. The modern concept of a function as we use it wasn't present, nor was there a clear, explicit distinction made between dependent and independent variables.
How did it describe the curve itself and these differentials, the Dade things?
A curve was visualized, implicitly at least, as an infinitengular polygon. That polygon with an infinite number of infinitely small straight sides. The tangent at a point was then seen as the extension of one of these infinitesimal sides.
Okay, that's a common intuitive picture.
Yes. But the way Leibniz actually defined the differentials, like dx and dv, he often used v for the ordinate, in this published paper was a major source of confusion, according to our sources.
Oh, so what was confusing about the definitions?
Well, for starters, he introduced dx, the differential of the abscissa, as being a finite quantity. He even described it as a segment arbitrarily fixed a priori and illustrated it as a finite length in the figure accompanying the paper.
Wait, finite. But the whole method relies on dx being infinitely small. Didn't you just say that?
Exactly. That's the problem. Our sources highlight this inconsistency. This initial finite definition of dx was never actually used in the applications or calculations presented later in the paper. For the method to actually work as described, ds absolutely had to be treated as infinitely small. This mismatch between the stated definition and the actual usage was baffling for readers.
Okay, that's definitely confusing. What about dv, the differential of the y value?
That was also problematic. He seemed to offer what appears to be a double definition for dv. One part described dv in terms of a ratio derived from those similar triangles. We discussed the characteristic triangle and the larger tangent ordinate subtangent triangle. He wrote something like, dv indicates the segment which is to dx as v is to xb, where v is the ordinate and xb is the subtangent.
Okay, a ratio linked to the geometry of the tangent.
Yes. And just to add to the fun, our source notes there was a typographical error in the notations for the subtangent, xb, right there in the paper, which certainly didn't help clarify things.
Oh, wonderful. A typo in a crucial definition.
Right. But the other part of the definition, or perhaps a different way he used dv, simply stated that dv is the difference of the v, meaning dv is the actual infinitesimal difference between two successive infinitely close y values, dv equals vx plus dx vx.
And that definition, the actual difference, is the one that makes sense for the calculus, right? Aligned with his Paris work.
Yes, that second interpretation, dv is the infinitesimal difference, is the one that aligns with his private Parisian manuscripts and is fundamentally necessary for the method's validity. The first definition, using the ratio, was more about the geometric interpretation used to determine the tangent line's slope, but it wasn't the fundamental concept of the differential within the calculation rules themselves.
So this ambiguity between defining dv via a ratio versus defining it as an actual infinitesimal difference combined with the finite versus infinitesimal dx issue, it made the very building blocks of the calculus murky from the start.
It's extremely murky. He would talk about differentials, dv dx, as infinitely small differences of two successive ordinate subsisters. but then relate them to finite quantities, like the ordinate v or subtangent xb, via the curve equation and the tangent geometry in a way that wasn't transparent or consistently defined in the paper itself.
So the definitions of the core symbols, D and NEFO wasn't the focus here, were ambiguous or even contradictory in places. What about the rules of differentiation, like how to find the differential of a product or a power?
He presented the rules, yes. He gave rules for differentiate constants, d, constants in the x, variables equal to each other. If yv, then d sin the ox, sums dy plus z times c to the a, differences, products, dqy, d axis d dx, and quotients, the standard rules we learned today.
Essentially, yes. But a critical point, heavily emphasized by our sources, is that these rules were presented without any proof or justification.
Just stated as facts, like magic formulas, pretty much just laid out there. And for the product and quotient rules specifically, he initially used a confusing system of double signs, combined in a specific way, that he would later abandon because it was unclear.
No proofs. Where are the proofs? Did he have them?
That's the thing. The proofs, or at least the justifications based on how infinitesimals work, do exist in his private Parisian manuscripts developed years earlier. These proofs typically involved algebraic manipulations, where terms like dx or products like dx dv were eventually discarded or neglected because they were considered infinitely smaller than the terms involving just dx or dv.
Ah, the classic discarding higher-order infinitesimals argument.
Exactly. But this crucial aspect of how infinitesimals were handled, in the proofs, the justification for ignoring these infinitely smaller terms, was deliberately hidden or omitted from the published 1684 paper, again, likely to avoid foundational criticism.
So he had the derivations, but he didn't show them, especially the controversial parts about manipulating and discarding these strange infinitesimal quantities.
Precisely. It's also interesting that Leibniz later wrote a manuscript responding to critics like the Dutch mathematician Bernhard Nieuwentyt, where he showed how the differentiation rules could potentially be justified without explicitly relying on infinitesimals, possibly using some concept of continuity or limits, though still not fully rigorous by modern standards.
So he was definitely aware of the foundational issues and thinking about alternatives even then.
Oh, absolutely. He knew the ground was shaky. But his initial published approach in 1684 prioritized getting the method and its capabilities out there over providing a complete, rigorous, potentially controversial explanation of why it worked.
That's a fascinating strategic calculation he made. What else did the paper cover besides the basic rules? Did he apply it?
Yes, he used the calculus to analyze important geometric properties of curves. He discussed how to determine where the ordinates, y values, are increasing or decreasing based on the sign of dv, how to find maxima and minima, how to determine intervals of concavity and convexity, and how to identify inflection points where curvature changes direction.
Standard applications we see in calculus today. Any issues there?
There were some initial rough edges. He implicitly assumed dx was always increasing positively when analyzing the sign of the differential dv. Our sources mention he made an initial erroneous statement about how the sign of dv related to whether the tangent pointed towards or away from the origin, a detail later corrected. He also initially overlooked some special cases, like inflection points, where the tangent might happen to be horizontal.
And for maxima and minima, did he get that right?
He correctly identified the necessary condition, dv0 at a maximum or a minimum point, assuming the tangent isn't vertical. This means the tangent line is parallel to the x-axis at such points. His focus was primarily on using the calculus to find the location of these extreme points, not rigorously proving their existence, which was often clear from the geometric context of the problem anyway.
But maybe not the full picture yet.
Right. Our sources note that the deeper understanding the fact that finding dv0 is necessary but not sufficient, and that the sign of the differential ratio, the derivative dv dx, must actually change from positive to negative for a maximum, or negative to positive for a minimum, as you pass through the critical point, wasn't fully clarified until the Bernoullis, and especially Levital, explained it more thoroughly in their subsequent work, or even later with Cauchy's more rigorous analysis involving second derivatives or behavior near the point.
So the core idea was there, but the subtleties needed more work. He also introduced the idea of second differentials in this paper, right?
Yeah.
DDV.
Yes, he defined second differentials, written as DDV or DD, as the differences of differences. He did this implicitly assuming that dx, the differential of the independent variable, was constant, ddx0, so ddx0.
Why introduce second differentials? What were they used for?
Primarily for analyzing concavity and identifying inflection points. He related the sign of ddv to the concavity up or down of the curve. He defined inflection points as places where the concavity-convexity exchange, or alternatively, as points where the prime differential, what we call the first derivative, dvdx, has a maximum or minimum.
Are those conditions correct?
They are necessary conditions, yes. However, our sources point out that in this early 1684 paper, Leibniz stated these conditions involving second differentials as if they were both necessary and sufficient for identifying an inflection point, which isn't always true. There are edge cases. This again would be refined and clarified later, notably in L'Hôpital's textbook.
So revolutionary concepts mixed with confusing definitions, missing proofs, some initial errors or oversimplifications. It really paints a picture.
It does. It's a mix of brilliance and, well, rushed and obscured presentation. Despite all these issues, though, he also made sure to showcase the power of his method. He applied the rules for powers, roots, and even composite functions, like a chain rule, to challenging curves. And importantly, he applied them to transcendent curves, like the cycloid.
The cycloid. Why was that significant?
Applying the calculus to the cycloid, the path traced by a point on a rolling circle, was a particularly clever and strategic move. René Descartes, the giant of the previous generation, had famously argued that such mechanical or transcendent curves should be excluded from the realm of rigorous geometry because they couldn't be expressed by finite polynomial equations.
So Leibniz was deliberately tackling something Descartes had deemed off-limits.
Exactly. By showing that his new calculus could easily find the tangent to the cycloid, a notoriously difficult problem that had occupied many great minds, he was demonstrating his method's superiority and broader applicability. It was a way to grab the attention of the mathematical community and say, look what my calculus can do. Our source even mentions that Christian Huygens, his old mentor, expressed great admiration for Leibniz's elegant cycloid tangent calculation in a letter written in 1690.
So he proved the method worked by solving impressive, hard problems, even if the explanation of how it worked was frustratingly unclear.
Precisely. That was the strategy. The paper concluded by demonstrating the calculus's power on 4 specific, difficult problems that were current challenges at the time. 1. Finding the tangent to a very complex algebraic curve involving fractions and radicals, something incredibly tedious or impossible with existing methods by Descartes, Fermat, Hud, or Sluis. Leibniz's method made it quick. 2. Solving a minimum problem related to the refraction of light, similar to one studied by Descartes and Fermat. Fermat's geometric method was notoriously laborious. 3. Tackling a type of problem Descartes had described to Fermat as being of insuperable difficulty, which involved finding tangents to a curve defined by an equation with 4 roots. Leibniz solved a similar, even more complex version involving 6 roots. 4. Solving an inverse tangent problem posed by Debun to Descartes, finding a curve given a property of its tangent, which Descartes had struggled with. Leibniz solved it elegantly in just a few steps using his calculus.
He was really throwing down the gauntlet, wasn't he? Showing his tool could solve the hardest problems faster and more elegantly than anyone else's.
That was clearly the intent. He wanted to impress and stake his claim. He closed the paper with a statement reflecting this pride and his vision for the future, a quote our sources emphasize.
These are only the premises of a more sublime geometry which extends to all other more difficult and most beautiful problems, also of mixed mathematics, which, without our differential calculus or the like, no one is capable of treating with equal ease.
A bold claim to end on. So, summing up this complex picture of the 1684 paper, it was groundbreaking in its potential, but undeniably baffling in its presentation.
Right.
Rushed, possibly due to the competitive threat from Schönhaus.
Likely.
Deliberately obscured, at least partly, to hide the controversial infinitesimals.
Strategic necessity, perhaps.
Containing ambiguous definitions, unproven rules, and some initial oversight.
Check.
And yet, demonstrating undeniable power through solving really hard state-of-the-art problems. That's the paradox of its debut. The external pressures and internal strategic choices resulted in a publication that was revolutionary in content but frustratingly opaque in form. It essentially announced the existence of a powerful new secret weapon, but didn't provide a clear user manual.
Okay, so the differential calculus, the eta part, is out there in 1684, causing confusion but also intrigue because of the problems it solved. What about the other half of the picture, the integral calculus, the eta part? When did that make its public appearance?
The stimulus for Leibniz's first paper, specifically addressing integral calculus, or calculus summatorius as he initially called it, the summation calculus, came a couple of years later in 1686. And interestingly, Just like the first paper, its publication seems to have been prompted by external events needing clarification.
Not another priority dispute, was it?
Sort of, yes, indirectly involving Tschirnhaus again. It was triggered by a book published in London in 1685 by the Scottish mathematician John Craig. Craig's book dealt with methods for finding areas under curves, quadrature methods. The key issue, according to our sources, was that Craig mistakenly attributed a paper on quadrature, which had been published by Tschirnhaus back in the Acta Eruditorum in October 1683, to Leibniz.
Oh, so Craig got the author wrong, giving Leibniz credit for Tschirnhaus's work on quadrature.
Exactly. And Leibniz, wanting to correct this erroneous impression and assure his own original methods for quadrature and their connection to his differential calculus received proper recognition, felt compelled to publish his own paper focused on the summation calculus.
So another publication driven by the need to clarify who did what. Where did this one appear?
It also appeared in the Acta Eruditorum in June 1686. The title was De Geometria Recondita et Analysi Indivisibilium atque Infinitorum.
More impressive Latin translation.
Something like about the deep geometry and the analysis of indivisibles and infinities. In this paper, he really stressed the significance of being able to handle transcendent curves, those tricky curves, not defined by simple polynomial equations and quadrature problems. He claimed credit for subjecting these more complex curves to analytical methods using his calculus.
And this is where he formally introduced the summation side, the integral calculus.
Yes. After first defining the differential expression for a geometric quantity called the subnormal, which is related to the tangent and the normal line, he formally introduced the concept of summation, or calculus summatorius.
The summation calculus.
Right. The name directly links back to that original core idea we discussed, finding areas by summing up many infinitely small quantities, essentially summing up the areas of infinitely thin rectangles formed by the ordinates, y values, and the infinitesimal differences of the abscissus, dx. And he confirmed the use of the easy sign, reiterating its origin from the words summa, meaning sum.
Okay, so he lays out the integration concept. Did he explicitly state the relationship between this new summation calculus and the differential calculus he'd published back in 1684?
Crucially, yes. This is a major point of the 1686 paper. He presented integration, summation, as the inverse operation of differentiation.
The inverse relationship.
Exactly. This concept that finding the area under a curve, integration, is the inverse process of finding the tangent slope of another related curve, differentiation, is the heart of what would later be formally recognized as the fundamental theorem of calculus. It establishes the deep, profound connection between the two seemingly different halves of the calculus.
So he laid out that fundamental inverse relationship clearly here in 1686. What kind of integrals did he work with in this paper? Were they like the definite integrals with limits or indefinite integrals with the plus c that we learn?
That's a good question. Our sources clarify that the integrals discussed in this paper and generally in his work at this time were primarily what we would now interpret as definite integrals, or perhaps more accurately, concerned finding a primitive function, an antiderivative, whose differential was a given expression.
So more focused on finding the area up to a certain point or finding one function that worked, rather than the general family of functions.
Yes. They weren't typically presented with the general constant of integration, plus c, explicitly in the notation the way we systematically teach indefinite integrals today. The source provides an example from Leibniz's work, using notation from the time which, when interpreted in modern terms, represents calculating an area from 0 up to a certain bound y. It looks something like year rests ahead equals y, where x is treated as a function of y here. This shows he was definitely thinking about calculating specific areas defined by limits, or finding specific functions whose differentials matched a given form, rather than just the general indefinite integral.
Got it. And by this point, 1686, did he acknowledge that his first paper from 1684 had been, well, difficult for people?
Oh, absolutely. He was clearly aware of the confusion. He actually opened this 1686 paper by acknowledging the difficulty readers had faced with his earlier work. Our source quotes him saying something along the lines of, "I have seen that many essays I published in Acta on the progress of geometry have been most appreciated. But, due to errors made in writing and two other reasons, some points were not fully understood. Therefore, I believe it will be worth adding a few remarks to clarify the previous articles herein."
Errors made in writing and other reasons. That sounds like a polite way of saying it was confusing, maybe hinting at the deliberate obscurity, too.
Could be interpreted that way, yes.
Yeah.
He definitely knew the 1684 paper had not been clear enough and clarification was needed.
Okay, so 1686 brings the integration side into public view, formally establishes the crucial inverse relationship, and shows he's aware people are struggling with the first paper. What about the third key paper mentioned in our sources, the one from 1693? What did that add?
The third key publication discussed is the Supplementum Geometriae Dimensori, which appeared in the Acta Eruditorum in September 1693. The title translates roughly to Supplement to Measuring Geometry. As the title suggests, this paper focused heavily on quadrature problems, the measurement of areas.
More on integration and areas, then. Did this paper introduce new concepts or mainly clarify old ones?
It did both, actually. A notable new concept introduced here was the quadratrix curve. He described how such a curve could be generated by a specific type of drawing motion, attractional motion, and its key defining property was that its ordinance, its I values, at any point, x, directly represented the accumulated area under a different given curves up to that same x value.
Ah, okay. So if you wanted to know the area under curve A from the start up to pi 5, you'd just look at the I value of the special quadratrix curve at pi 5.
Precisely. It was a clever geometric way of visualizing and representing the process of integration or finding accumulated area. And a major theoretical result presented in this 1693 paper was proving that all quadrature problems could be reduced to inverse tangent problems.
He linked areas and tangents again, but this time showing area problems could be turned into tangent problems. How does that work?
It essentially reinforces the fundamental theorem from the other direction. Our sources interpret this connection in modern terms like this. If you have a function y that represents the accumulated area under a curve defined by another function z, say y equals z dx, where y is the area function and z is the curve being integrated, then the function z itself is simply the derivative of the area function y with respect to x, z equals a dx.
Right. The rate of change of the area is the curve you're finding the area under.
Exactly. So finding an area, a quadrature problem, is equivalent to finding a function, the area function or primitive, whose derivative, tangent slope property, is the given boundary curve z. This means solving an area problem is the same as solving an inverse tangent problem, finding the function when you know its derivative.
That really hammers home the unity of the two halves of calculus. Did this paper period also show a better understanding of the constant of integration, the plus E idea, even if the notation wasn't there?
Yes. The sources indicate that while the distinct notation for definite versus indefinite integrals wasn't standardized as it is today, Leibniz, and especially the Bernoulli brothers, who were deeply engaged with his work by this time, as we'll discuss, absolutely understood the concept. They knew that for any given differential expression, like dAz dx, there wasn't just one primitive function now, but an infinite family of them, all differing only by an additive constant.
They knew about the family of curves with the same derivative.
Yes, and critically, they also knew how to use any one of those primitives to calculate a definite integral, like finding the area between xa and xb, by evaluating the primitive function at the upper bound a and the lower bound a, and simply subtracting the results. FBFA.
So they had grasped the core functional concept behind the fundamental theorem and constants of integration, even if the modern symbolism wasn't fully developed yet.
Correct. They understood the mechanics and the implications. And interestingly, showing his continued awareness of the communication challenges, Leibniz wrote to the French philosopher Nicolas Malebranche in 1693, around the time this third paper was published, again acknowledging the issues with his earlier essays. Our source quotes him saying something like, "If one day I will have the opportunity, I will present the rules and use of this calculus a little more clearly than I did in the Leipzig Acta, because many mistakes are responsible for making the writing obscure, and for this reason I believe that many readers did not understand a thing."
Many readers did not understand a thing. He really knew he hadn't nailed the explanation the first time around, didn't he? Even by 1693.
He was very aware. So yes, these later papers from 1686 and 1693 start filling in the picture more completely. They introduce the integration side more formally, make the crucial inverse relationship explicit, show the deep connection between finding areas and finding primitive functions, solving inverse tangent problems, and hint at the understanding of multiple primitives.
It sounds like they show the evolution of his own thought and presentation, and his continued effort to make the calculus understandable, even if the style likely remained challenging for many readers compared to, say, a modern textbook.
Absolutely. The reduction of quadrature to inverse tangent problems was a significant theoretical achievement reported in the 1693 paper, demonstrating the deep structural unity between the two major classes of problems that calculus was designed to solve. It helped solidify the calculus as a coherent system.
Okay, so we've seen the genius invention emerge in Paris, the incredibly obscure first paper drop like a puzzle in 1684, and then these subsequent efforts in 86 and 93 to clarify the integration side and the fundamental connections. What was the immediate reaction from the wider mathematical world to that baffling 1684 publication? Section 4 in our outline gets into that early reception, the mystery, and the masters who cracked it.
Right. As we've already heavily hinted, the initial reaction wasn't exactly widespread adoption and immediate understanding. Far, far from it. The sheer brevity, the confusing definitions, the missing proofs, and the likely deliberate obscurity of the 1684 paper left many readers, even highly accomplished mathematicians of the day, utterly perplexed. Our sources repeatedly state that it was widely viewed simply as an enigma.
An enigma. That word keeps coming up. A revolutionary idea presented as a mystery to be solved.
Indeed. It wasn't just difficult, it seemed intentionally cryptic to some. But fortunately, not everyone gave up immediately. Some persistent and truly brilliant minds decided to try and penetrate this mystery, and chief among them, the first and arguably most important, was Jacob Bernoulli.
Jacob Bernoulli, one of the famous Bernoulli brothers from Basel, Switzerland, a mathematical dynasty.
Exactly. Jacob Bernoulli, who lived 1654-1705, would become one of the earliest and most important proponents and developers of the Leibnizian calculus on the European continent. And according to our sources, he was actually the first person to formally articulate just how difficult Leibniz's 1684 paper was to understand.
How did he do that? Did he publish a critique?
No, he wrote directly to Leibniz himself in a letter dated December 15, 1687. That's about 3 years after the paper came out. And shortly after Jacob was appointed to the mathematics chair at the University of Basel, he frankly expressed his difficulty and asked for clarification. Our sources provide a fascinating quote from this letter, where Jacob Bernoulli essentially lays down a challenge to Leibniz. He writes something like, "Therefore I believe that you, Messer, are concealing here the traces of a more sublime form of mathematics."
Concealing here the traces. He's calling him out.
He is. He makes it clear he's seen the impressive results. You and Messer Tschirnhaus have discovered so many and such important things, but he cannot grasp the method itself from the paper. Then comes the offer, the plea almost. "I wish to learn about the mathematics by means of which you and Messer Tschirnhaus have discovered. If you will deem me worthy of partaking a ray of light of your method, once I have been informed of your discoveries, I will become not only a simple admirer, but your most devoted appraiser and propagator."
Wow, that's quite direct. Basically, show me how this incredible thing works, explain the mystery, and I'll become your #1 champion and promoter. What did Leibniz say? Did he immediately send him a detailed explanation and win over his first major disciple?
Well, unfortunately for Jacob Bernoulli, Leibniz couldn't provide that immediate detailed response. As we mentioned earlier, Leibniz was heavily engaged in extensive travels throughout southern Germany, Austria, and Italy during this period. He was undertaking major historical research for his employers, the House of Brunswick-Lüneburg. He was simply too busy, often away from his papers and notes, to sit down and provide the kind of in-depth explanation Jacob needed.
That's frustrating. A bit of bad luck for Jacob just as he's ready to dive in. Did he just wait around for Leibniz to eventually get back to him years later?
No, he didn't. And this is where Jacob Bernoulli's brilliance and tenacity really shine through. Our sources emphasize that Jacob persevered in his intent. Because Leibniz couldn't provide immediate help, Jacob took it upon himself to wrestle with the obscure 1684 paper, combine it with his own understanding of related infinitesimal methods that were circulating, and just keep hammering away at it.
He decided to crack the enigmas himself.
Yes. And through sheer hard work, intellectual power, and brilliant insight, he succeeded. He managed to penetrate the secrets of the calculus largely on his own.
He figured it out independently from that baffling paper. That's incredible.
It really is a testament to his ability. And crucially, our sources add a key detail from Jacob's own later correspondence that sheds light on the next step. Jacob Bernoulli explicitly stated in a letter he wrote to Leibniz much later, on November 15, 1702, during a discussion about his brother Johann's claims regarding who learned what first, Jacob wrote, "You would have noted that I, not he, penetrated the mysteries of your calculus first, and that I them taught them to him."
So Jacob figured it out independently first, and then, critically, he taught his younger brother, Johann Bernoulli. That's how the Bernoulli brothers, who became the absolute powerhouses of calculus on the continent, got their start.
Exactly. Jacob's perseverance wasn't just a personal intellectual achievement. It was the crucial act that unlocked the calculus for his brother and, through their subsequent teaching and prolific writing, for future generations across Europe. Jacob didn't hide the difficulty either. He openly acknowledged the challenge of Leibniz's original paper to his own readers in a publication of his own, Specimen Calculi Differentialis, a sample of the differential calculus, published in the Acta Eruditorum in January 1691, which was one of the very earliest papers by someone other than Leibniz applying the differential calculus. Jacob explicitly stated the need to show the use and application of the method. He wrote this was necessary, and I'm paraphrasing slightly, so that if by chance my readers have not adequately understood the thoughts of the sharp scientist Leibniz from the words he published in Acta in 1684 due to excessive brevity, they may learn his method of application here.
So Jacob's own work essentially served as one of the first public guides or tutorials on how to actually do calculus, filling the massive explanatory gap left by Leibniz's opaque initial paper.
Precisely. He wasn't just using it, he was demonstrating how to use it, showing the world not just the tantalizing idea, but the practical application and methodology. The difficulty of Leibniz's 1684 paper was widely recognized by other contemporaries as well, confirming Jacob wasn't alone in his struggle. Fontenelle, the secretary of the French Academy of Sciences, in his eulogy for Jacob Bernoulli written around 1204-1706, explicitly stated that Leibniz's 1684 paper concealed both the art and the method. It hid the technique.
And Johann Bernoulli, the brother Jacob taught, did he agree it was tough?
Johann Bernoulli was equally clear about the initial paper's nature, though perhaps slightly downplaying the duration of the struggle compared to Jacob's account years later. In his autobiography, Johann described the 1684 paper as more an enigma than an explanation. But then he added, however, this was sufficient for us, meaning Jacob and Johann, to grasp the entire secret in a few days.
A few days? That sounds impressively fast, even if Jacob's account suggests he cracked it first and then taught Johann.
Yes, there's a slight difference in emphasis, perhaps, but the core point remains. They both acknowledged the paper was an enigma, yet they did manage to grasp it relatively quickly compared to everyone else, become the first true masters of the Leibnizian calculus after Leibniz himself. Regardless of the precise dynamics or timeline between the brothers, the key outcome is they did grasp it when most others could not.
It's still remarkable that even for these brilliant minds, renowned mathematicians in their own right, it took significant independent effort to decode Leibniz's first publication. And even Huygens, Leibniz's former mentor who knew him well, found it difficult initially, didn't he? You mentioned that earlier.
Yes, that's a crucial point. Even Christian Huygens, who had personally guided Leibniz's early mathematical studies in Paris and presumably understood Leibniz's way of thinking better than most, initially found the 1684 paper baffling. In a letter to Leibniz dated August 24th, 1690, 6 years after the paper appeared, Huygens admitted, I read something about your new algebraic calculus in the Leipzig Acta, but I found it obscure and did not study it sufficiently to gain understanding.
Even his old teacher was lost at first glance. That really underscores the difficulty.
It does. Though Huygens, being Huygens, did return to it. In a later letter from October 9, 1690, just a couple of months later, he wrote that he insisted, meaning he dedicated serious, focused effort for 2 full days to understand the paper. And only then, after 2 days of hard study, did he find it very good and very useful. But the conceptual difficulties seemed to linger even for him. As late as September 1693, 9 years after the initial publication, Huygens was still writing to Leibniz asking for clarification on specific aspects, like the meaning and use of ddx, the second differential of x, which Leibniz usually assumed to be 0. This shows that even for a genius like Huygens, fully understanding all the details and nuances of Leibniz's new system was a continued effort, not an instant revelation.
So if Leibniz's own mentor and brilliant independent minds like the Bernoullis struggled this much, often for years, it's absolute no surprise that the wider mathematical community was largely left scratching its head, completely unable to make sense of it from that first paper alone.
Absolutely. This period underscores just how profoundly novel and conceptually challenging the calculus was at its inception, and perhaps how poorly served the initial publication was in making its revolutionary ideas accessible. Historians of mathematics have consistently noted this obscurity in the slow initial uptake. Montucla, a prominent 18th century historian of mathematics, stated that years after 1684, the differential and integral calculus remained essentially a mystery for most geometers.
A mystery for years.
Yes, and more recently, the historian Joseph Ehrenfried Hoffmann suggested that the 1684 paper might have been, as we discussed, deliberately formulated in such a concise way that an unsuspecting reader could scarcely, if ever, grasp the fundamental ideas. And another historian, Revaux, writing in 1950, echoed this, calling the 1684 essay most obscure and difficult, concluding that even Leibniz's later clarifying papers only managed to enlighten a few exceptionally gifted readers, like the Bernoulli brothers. Even great mathematicians like Christian Huygens, Revaux argued, would never fully comprehend the method, which might be a slight exaggeration for Huygens, but it captures the general sentiment of extreme difficulty.
It surely was an enigma then. This paints such a vivid picture. A revolutionary idea is born, but it's presented in a way that's almost impenetrable. It required immense personal effort, genius, and perseverance from dedicated individuals like Jacob Bernoulli to decipher it, essentially reverse engineering the method from the clues Leibniz provided.
It highlights a crucial aspect of scientific progress, doesn't it? It's not just about the moment of invention, that eureka moment. It's also about the arduous, often messy process of communication, dissemination, understanding, validation, and clarification by a wider community. The Bernoullis didn't just passively receive Leibniz's work, they had to actively wrestle with it, decode it, master it, and ultimately build upon it themselves, becoming independent experts and innovators within the new framework. It was active co-creation as much as reception.
Okay, so the code has been cracked primarily by the persistent Jacob Bernoulli, who then brings his brother Johann into the fold. They understand it. They're starting to use it. How does this powerful but initially obscure method go from being understood by just a handful of people in Basel and Hanover to becoming the dominant mathematical language across continental Europe? That brings us to section 5. From enigma to empire, the spread of the Leibnizian calculus.
Right. Well, Leibniz himself was acutely aware, right from his Paris years, of the revolutionary potential of his invention. He knew he hadn't just found clever tricks for solving specific problems. He believed he had created a general algorithm, a new and universal mathematical language, a calculus that could tackle a vast range of problems with unprecedented ease and power.
He had the vision. But given the disastrous reception of the 1684 paper in terms of clarity, he clearly couldn't spread it effectively all by himself. He needed help.
Precisely. He was extremely fortunate, perhaps even strategically astute, in finding dedicated champions and effective popularizers for his calculus. The Bernoulli brothers, Jacob and Johann, were absolutely critical in this. They didn't just understand the calculus, they became its most brilliant early practitioners, extending its methods, solving spectacular new problems with it, and acting as its most enthusiastic advocates and teachers on the continent.
They were the technical powerhouses.
Exactly. And then there was another key figure, Guillaume François Antoine, the Marquis de l'Hôpital, a wealthy French nobleman and amateur mathematician. He played a crucial, different role as the calculus's first great popularizer by writing the first textbook. Together, these figures, the Bernoullis as the champions and developers, l'Hôpital as the popularizer, were instrumental in promoting and advancing Leibniz's methods at the very highest level of European mathematics.
So how did they actually get the word out? Was it just through more obscure journal articles that only experts would read? How did it gain wider traction?
The most effective method of popularization, especially in the early years, wasn't just trying to explain the rules abstractly, which Leibniz's first papers had struggled so much with. Instead, it was demonstrating the sheer power and utility of the calculus through the impressive results it could achieve.
Show, don't just tell.
Exactly. The Bernoulli brothers, Leibniz himself, and others began publishing solutions to difficult, high-profile, open mathematical and physical problems of the day in prominent scientific journals like the Acta Eruditorum and the Proceedings of prestigious scientific academies, particularly those in Paris and later Berlin.
What kind of problems were these that caught everyone's attention?
There were often cutting-edge challenges that had stumped mathematicians using older geometric or algebraic methods. Our sources list several famous examples. Finding the exact mathematical shape of a uniform, hanging chain or cable suspended only by its ends, the catenary problem, solved using calculus. Determining the curve down which an object will slide between 2 points in the shortest possible time under gravity, the Brachistochrone problem. Johann Bernoulli famously posed this as a challenge and solved it elegantly using calculus, showcasing its power over other methods. Calculating the shape of a sail filled by wind, the Villery problem. Finding a curve called a pericentric isochrone related to orbital motion. Determining the shape of a bent elastic rod or beam, the Elastica problem. Solving complex isoperimetrical problems, which involve finding shapes that maximize or minimize some quantity, like area, while keeping another quantity, like perimeter, fixed. Jacob Bernoulli made major contributions here.
These sound like the really big, famous mathematical physics challenges of the late 17th century, the kind that would make people sit up and take notice if someone had a new way to solve them.
Exactly. These weren't just abstract exercises. They were problems rooted in mechanics, optics, and geometry that the best minds had wrestled with. And the Leibnizian calculus provided the tools to finally crack them, often with surprising elegance and efficiency compared to the cumbersome methods used before.
And it wasn't just these famous challenge problems.
No. Beyond these headline-grabbing applications, the calculus offered powerful new general techniques for pure mathematics as well. Things like developing methods for solving differential equations that actually involve the differentials dx and dy themselves, which arise naturally in many physical problems. Systematically constructing and analyzing complex curves that weren't easily defined by simple algebraic equations, the so-called transcendental curves like the cycloid or logarithmic curves. Developing systematic methods for integrating various types of mathematical expressions, both rational and irrational. Calculating the precise arc length of curves, rectification, which was another notoriously difficult problem.
So they weren't just talking about how great the calculus was. They were actively using it to push the frontiers, to blow past the limits of existing mathematics and physics, and solve previously intractable problems left and right.
That was absolutely the key to its spread. The undeniable utility of the method in solving these significant problems across both pure and applied mathematics made it incredibly attractive. Scholars and practitioners in a growing range of fields, optics, mechanics, architecture, acoustics, astronomy, hydraulics, even medicine, eventually began to see the potential of these new techniques. Our sources describe them finding the Leibnizian methods useful, nimble, and elegant for tackling their own specific problems. The results spoke for themselves, creating a buzz and a demand to learn this powerful new tool.
And Leibniz himself wasn't passive in this process of dissemination. He actively worked to spread his ideas too, didn't he? He didn't just invent it and leave it to others.
Oh no, he was, as our sources put it, the first and most important champion of diffusing his own calculus. He clearly saw it as one of his major contributions and wanted it to flourish. He actually had ambitious plans to write a comprehensive treatise himself, tentatively titled Scientia Infiniti, Science of the Infinite, that would explain his procedures clearly and rigorously.
Did that ever get published?
Unfortunately, no. Like many of Leibniz's grand projects, this major work on calculus never came to fruition amidst his countless other activities. However, he was reportedly delighted and strongly supported the publication of the first textbook on differential calculus, which filled that gap.
The one by the Marquis de l'Hôpital you mentioned.
Yes. Guillaume-François Antoine, Marquis de l'Hôpital's book, Analyse des infiniment petits pour l'intelligence des lignes courbes, Analysis of the Infinitely Small for the Understanding of Curved Lines, published in Paris in 1696. This was a landmark event. It was the very first systematic textbook explaining how to use the differential calculus. And crucially, it was explicitly based on Leibniz's methods, and, as history later revealed perhaps controversially, heavily based on lessons that Johann Bernoulli had been paid to give to the Marquis in Paris in 1691-1692.
So L'Hôpital essentially published Johann Bernoulli's lectures.
That's the historical consensus, yes. L'Hôpital acknowledged Johann's help in the preface, but presented the work largely as his own. Regardless of the authorship issues, this book played an absolutely crucial role in making the powerful techniques of the calculus accessible to a much wider audience beyond the handful of geniuses who could decipher Leibniz's original papers or learn directly from the Bernoullis.
And Leibniz was okay with this. He supported L'Hôpital's book.
Yes, Leibniz expressed his satisfaction with it. He recognized the need for such a textbook. He later stated that he had willingly shared his invention with people like the Bernoullis, precisely because he knew their elegant and very profound applications and further developments were so effective in boosting the acceptance and spread of the calculus across scientific fields. He seemed to prioritize the spread of the idea over strictly controlling every aspect of its publication.
It seems quite remarkable, almost generous, that he was so willing to share credit and allow others like the Bernoullis and L'Hôpital to run with his ideas, especially given the potential for later priori disputes over the invention itself, which famously did happen with Newton.
It does seem that way from the evidence presented in our sources. They include several quotes from Leibniz that illustrate this philosophy of sharing, collaboration, and perhaps strategic delegation, which was instrumental in the calculus's rapid spread on the continent. For instance, writing to Antonio Magliabechi, a famous Italian librarian and scholar, in 1692, Leibniz explained his approach, citing his numerous other commitments. I have so many different kinds of occupations to attend to that I gladly entrust this terrain of developing the calculus to the cultivation of my friends.
gladly entrust his terrain. He saw it as fertile ground for others to work in, not just his private garden.
Indeed. And when discussing the solution to the catenary problem, where others had successfully applied his calculus, he expressed genuine pleasure, writing, "But it is a very great pleasure for me to see the seeds I have sown bear fruit in others' gardens too."
That's a lovely metaphor. He saw his ideas not as closely guarded private property, but as seeds capable of flourishing when cultivated by others.
Exactly. And perhaps the most explicit statement of this philosophy comes in a letter to L'Hopital himself in 1699. Leibniz compared his own role to that of an inspirer or toolmaker, rather than the sole user of the tool. He wrote, "Moreover, as I am often more inclined to provide inspiration for discoveries than to make them, acting as a whetstone which, though it does not itself cut, is in the habit of making iron sharp, I hope I may be allowed sometimes to present things related either to calculations and reasonings or to execution, and to let others judge whether they are worth pursuing."
He saw himself as the whetstone, sharpening the minds of others like the Bernoullis and L'Hopital, enabling them to do the cutting-edge work. That collaborative spirit, or at least that willingness to let others build on his foundation, must have been incredibly key to its rapid adoption.
It seems to have been a very deliberate and effective strategy for diffusion. Leibniz also actively used his incredibly extensive network of contacts and correspondence across Europe. He was one of the most connected intellectuals of his time to promote the calculus. He worked to place key figures who understood and championed his methods in influential academic positions.
Strategic appointments.
Yes. For example, our sources mention he helped ensure that Jacob Hermann, who was a student of Jacob Bernoulli, and later Nicholas Assert Bernoulli, who was Jacob's nephew, both secured mathematics professorships in Padua, Italy. This was a major center of learning, and these appointments were crucial for introducing the Leibnizian calculus into the Italian universities, where different traditions had held sway.
Planting his proponents in key academic centers. Clever.
Very strategic. And as we mentioned, Johann Bernoulli was instrumental in introducing the calculus into France, starting around 1691, particularly through his connections with the influential intellectual circle surrounding the philosopher Nicolas Malebranche and the Oratorian religious order. Johann's direct, paid lessons to the Marquis de L'Hopital, then led directly to that foundational 1696 textbook, which spread the methods widely in France and beyond. Malebranche's influence in turn helped pave the way for the first French works focusing specifically on integral calculus by authors like Louis Carré in 1700 and Charles Renaud in 1708.
So it really was a multi-pronged, almost orchestrated effort, wasn't it? It took Leibniz's initial genius and his strategic willingness to share. It took the Bernoullis' incredible skill in deciphering, mastering, applying, and extending the methods to solve those high-profile problems. It took L'Hopital's crucial role in writing the first accessible textbook, based heavily on Johann's work. And it took the active networking, teaching, and placing of proponents by Leibniz and his circle to really spread the knowledge across the continent.
Absolutely. The transformation of the Leibnizian calculus from an obscure, difficult-to-understand publication into a widely adopted and indispensable tool of science and mathematics wasn't solely the result of the brilliance of the invention itself. It stands as a testament to the combined power of clarification, demonstrated utility through spectacular problem-solving, effective pedagogy, like L'Hopital's book, and enthusiastic propagation by a network of brilliant and dedicated individuals working together, formally or informally. It wasn't just discovered, it was actively built into the mathematical landscape by this collaborative, multi-generational effort.
It's a powerful story, not just about math, but about how scientific ideas truly take hold and spread. They need not just the original inventor, but also those crucial champions who can clarify, apply, teach, and build upon the initial vision.
Indeed. Leibniz's approach to sharing his invention, his whetstone philosophy as he put it, stands as a significant, perhaps defining factor in the rapid and ultimately dominant success of his calculus across continental Europe in the early 18th century.
Wow. We've covered a remarkable journey today. We started with Leibniz's rather unlikely path to advanced mathematics, spurred on by Huygens in Paris. We saw that spark of insight connecting sums and differences in number sequences to the geometry of curves via infinitesimal.
The core inverse relationship.
Right, leading to the invention of differential and calculus. Then we saw the dramatic, rushed, and deliberately obscure debut of the differential calculus in that tiny, baffling 6-page paper in 1684, truly an enigma, even to the experts of the time.
A confusing start, to say the least.
We looked at the subsequent papers in 1686 and 1693, where Leibniz started to clarify the integral side, formally state the inverse relationship, the fundamental theorem, and connect area problems back to tangent problems, though still perhaps not with perfect clarity.
Filling in the picture piece by piece.
And we saw how brilliant minds like Jacob Bernoulli had to literally struggle and decipher the initial mystery almost entirely on their own before teaching others, like his brother Johann. They became the crucial figures who cracked the code.
The key translators and developers.
Exactly, and how they, alongside figures like de L'Hopital, who wrote that first textbook, became the champions who demonstrated the overwhelming power of the calculus by solving major scientific problems, popularizing the methods, and strategically spreading the knowledge throughout Europe via teaching and networking.
It's really a journey from a private intellectual breakthrough, communicated initially as a published puzzle that few could solve, to eventually becoming the essential, indispensable language for describing change, motion, and accumulation in science and engineering.
And why does this history matter to you, the listener, today?
Well, because every single time you encounter calculus, whether you're studying physics or engineering, working with complex financial models or analyzing data, building computer simulations, designing algorithms, or even just marveling at the realistic physics or graphics in a modern video game or movie, you are seeing the living legacy of these very ideas.
It's everywhere. It really is. You're seeing the end point of Leibniz's initial insight, yes, but also the result of that difficult struggle to communicate something truly new, the confusion it initially caused, and the immense, often unsung work of those like the Bernoulli brothers who persevered, decoded it, extended it, and dedicated their lives to developing and propagating this incredibly powerful tool.
A powerful reminder, I think, that even the most elegant and seemingly fundamental mathematical concepts that we learn today often had incredibly messy, imperfect, and highly human beginnings. They rarely spring forth perfectly formed like Athena from Zeus's head. They're forged through struggle, clarified through error and debate, and spread through the dedicated, often collaborative effort of a community over time.
Some key takeaways to reflect on, maybe? The sheer power of finding the right notation like eat and d, even if it's presented confusingly at first. The fundamental elegance and importance of that inverse relationship between differentiation and integration. The bedrock of the whole calculus. The critical importance of sheer perseverance when faced with something profoundly difficult and new, like Jacob Bernoulli tackling that obscure 1684 paper.
Absolutely.
And maybe above all, the absolutely vital role of communication, teaching, collaboration, and demonstrating practical utility in transforming a brilliant but inaccessible idea into a widely adopted tool that genuinely changes the world.
All crucial lessons embedded in this specific history.
So here's something to ponder as we finish this deep dive. Considering just how obscure and seemingly incomplete Leibniz's initial publication actually was, and the fundamental conceptual difficulties surrounding the idea of infinitesimals that he wrestled with and partly concealed, what does this specific history tell us about the real, day-to-day, often messy, imperfect, and sometimes intensely collaborative process of mathematical and scientific discovery itself? How does that often chaotic reality contrast with the clean, rigorous, polished, and seemingly inevitable finished results that we typically learn about in textbooks or classrooms today?
It certainly gives you a very different, maybe more realistic perspective on how these towering intellectual achievements actually come into being, doesn't it? Less magic, more hard work and human interaction.
It really does. And that's been our deep dive into the fascinating and initially quite enigmatic origins of Leibniz's calculus.